Okay, so now we're going to start the last of the 4 measurements of concentration. And this is called molality, which sounds a lot like molarity. In fact, it is the same except for 1 letter. And because of this, and the fact that the formulas are similar, people get these 2 mixed up. So we have to be aware of the difference here. And that is that the denominator of molarity, as we said, is liters of solution. And the denominator for molality is kilograms of solvent. So the denominators of these 2 fractions, for molarity and molality, are the difference. And it's difference not just in what it's measured with, it's what you are actually measuring. The solvent is just the, if you will, the liquid part, if you're dissolving solid. If you're looking at the solution for molarity, it's the 2 of them added together. This is by itself. Solution are solute and solvent all mixed together. In a volume, this is in a mass. And this manifests itself later on when we start going through the last 3 sections, which deals with our ability to go back and forth between 2 ways of measuring concentration. So, here's the formula. You notice also that we're using a little m instead of a capital M. Also, we're going to use that little m as the label instead of moles per kilogram, like you would expect. It's going to be little m, but you still read it as moles per kilogram, like we did with the molarity. And the best way to understand this is by looking at an example of how we measure this. So in this case, what is the molality of 17.1 grams of lauric acid, or alcohol rather, which is that formula right there, in 165 grams of ethanol, and that is the formula for ethanol. Now, one of the formulas we need, the other we don't. So you have to, again, you have to remember what that formula is telling you to figure this part out. So let's put the formula here. M equals moles of solute over kilograms of solvent. You know, that's the formula that's going to be involved here. Let's also write down the information that's given to us in the problem. We are given here 17.1 grams and 165 grams. Okay, so 17.1 grams of lauric alcohol. And of course, I forgot already because I'm thinking of 10 million things at once. 165 grams of ethanol. Okay. So the question is here, which one of these 2 values do we actually need to know what the molecular formula is? Well, the best way to answer that question is look up here and see which one involves moles, because that's going to involve the periodic table. Our solute is our lauric acid. So we got to change that to moles. So we'll put 1 mole on top. And lauric alcohol, I should know this, but I can't off the top of my head. C12H45OH. Okay, that seems rather odd, but whatever. So we have 12 carbons, so it's 12 times 12.0, plus 25 hydrogens, 25 times 1.01, plus oxygen, 16.0, plus 1 more hydrogen, 1.01 grams. Okay, and the ethanol, because it's in kilograms and not moles, we don't care what the formula for ethanol is. All we have to do is change that to kilograms. So 1 kilogram over 1,000 grams. And of course that's going to be 0.165 kilograms, because when you divide by 1,000, you move the decimal point over 3 places. So we go back to the script here to see the numbers that we got for that. And when I divide those 2 out, as it was written, it's 0.273. And again, little m means moles per kilogram. And it doesn't mean meters here. You have to know the context at which these letters are being used for. This is in a concentration context, so that tells you that we're dealing with molality and not meters. Okay, here's another example. How much water must be added to 3.5 grams of fructose to give a 0.125 mole per kilogram solution? Okay, so we're dealing with, see if I can actually remember this, no guarantee. 3.5 grams and 0.125 meters. Okay, 3.5 grams, 0.125 moles per liter. 3.5 grams, 0.125 moles per liter. 3.5 grams and 0.125 moles per liter. Moles per kilogram, right? That's the worst G ever written in history of mankind. All right, so. So we got fructose here, which is C6H12O6, so we got to change this to moles. 1 mole on top. And we got 6 carbons, so 6 times 12.0 plus 12 hydrogen, so 12 times 1.0, 1 plus 6 oxygen, 6 times 16.0, all in grams. And so we plug this into the formula. M equals moles of solutes over kilograms of solvents. Well, solvents. We know that the solute is our fructose. Does anybody know what fructose is? Biology people, hello, hello, hello. It's fruit sugar. So when you bite into an apple or a pear or orange Indian, it's sweet. That's the taste you're getting. It's not sucrose, table sugar, and it's not glucose, which is the stuff that the plants use to feed the leaves feed the plants with that to create the oxygen and the glucose. It's created from the carbon dioxide and the water from the ground. Okay, and solvent here is water. So this is obviously what we're going to be really focusing on here. So this is going to give us 0.125 here. And whatever this is going to go right there. And that means our unknown is going to be in the denominator. Woo! We got an issue here. Now in the last video I explained to you how having a variable in the denominator is a real issue. So we're going to put a 1 here and cross multiply, and that will take care of our issue with the x in the denominator. And so when the smoke clears, we are going to get 0.125 moles per kilogram equals 0.0194 moles divided by x. And by the way, danger, Will Robinson, danger, danger. There's a TV series. I won't say it was great. I would say it was great in irritating people. It was one of the most irritating science fiction shows I've ever seen. The special effects were horrific, but still I managed to watch every episode of it. Because it was science fiction. I was crazy about this stuff at the time. But they had this robot. It was kind of like a version of Space Family Robinson instead of Swiss Family Robinson, which I'm sure most of you have never heard of before anyway. But they would go traveling around the universe, visiting planets, and the robot would start giving warning. Will Robinson was one of the kids in the family, and his arms were like this, danger, Will Robinson, danger, 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 and so they had to get out of Dodge as quickly as possible. So here's the danger. The danger is this thing right here. Okay, now again, use the proportion like I showed. You can also flip-flop. And what I mean by that is you take the x to the 0.125 and switch them around, which is what you end up doing in the proportion anyway. So, but if you can't remember that, just do the proportion thing and life is all good. And when you're done, you get 0.155 kilograms of water. And if you want it in grams, just multiply by 1,000 grams per kilogram, you get 155 grams of water. Okay, so the mathematics is a little tricky. if you get an excellent denominator, but use whatever makes the most sense to you, and life is all good. Practice problems, page 547, problems 46 and 48. Good luck.